All right, we've got our senior skip day Friday quiz. Don't worry, it's up on YouTube. You can do it at your leisure. It says, a star has a luminosity that is known to be 4.8 by 10 to the 29 watts. A scientist observing the star finds that the radiant flux intensity of light received on Earth from the star is 2.6, and we read this as nanowatts per square meter. Name the term used to describe an astronomical object that has known luminosity. Once again, name the term used to describe an astronomical object that has known luminosity. This is called the standard candle quiz for a reason. So that's called a standard candle. Earlier this year, we learned about dark energy and Dr. Brian Schmidt's Nobel Prize winning work, where he used type 1a supernovae to sort of measure the Hubble constant, right? And so type 1a supernovae could be thought of standard candles, right? Because we sort of can know how bright they are intrinsically, and then how bright they appear to us on Earth gives us an idea about how far away they are. So we want to now determine the distance of the star from Earth. So this was one of the first equations that we looked at this year. Flux, remember, is how much power is incident upon a square meter of collecting area, right? So we can always measure this here on Earth. It's like, how bright does it appear to us? So the radiant flux intensity is the apparent brightness. The luminosity is the actual brightness, and it's given in watts here. And remember that because we have stars that radiate their energy out in all directions, right? And it's actually a sphere, right? So a planet that is a certain distance away is receiving but a fraction of the total luminosity, right? So that luminosity is spread out over the area, the internal surface area of the sphere, which is 4 pi d squared, where d is sort of its radius. And that's the distance, from the star to us here on Earth. You've got to be able to convert nano, okay? So to know the metric prefixes to convert this nanowatts, right? So we can have consistent units. So let's go ahead and rewrite this to make D the subject, because that's the thing that we're solving for. So the first thing I would do is multiply both sides by 4 pi d squared. And then divide both sides by 4 pi times the flux. From here on out, I'll just use the lowercase letter f for flux. And so we've got 4's going away, pi's going away, flux cancels out, but I got to divide this side by 4. All right, multiply that. I'm trying to get this all by itself. So multiply that, got L. Over here, divide by 4 pi flux, divide by 4 pi flux. So now we've got L over 4 pi times the flux, all right, equal to d squared. And so we can take the square root of both sides. So the distance should just be the square root of the luminosity divided by 4 pi times flux. And indeed, I think we even saw this in general. Like if we need to solve for the distance of something and we know the luminosity and we know the flux, we could plug it in like this. So we know that the luminosity is 4.8 by 10 to the 29 watts. We know that we got 4 and pi down here, and the flux is given as 2.6 times 10 to the negative 9. So nano means billion. So 10 to the negative 9 is the order of magnitude, and then is watts per meter squared are the units. When we divide, we'll cancel out watts. And when we take the square root of all of this, we'll also take the square root of meters squared, and we will get meters of distance. And so that's nice to sort of see that the units work out to give us what we would expect for distance in meters. And now it's some button pushing here. I'll show that to you here on the screen. All right, we got a nice scientific calculator there. And we'll start here in the numerator, 4.8 times 10 raised to the 29 equals. So there's a lot of watts of power. And again, we know this because it's a standard candle, right? So it's known to be this. And so standard candles just have known luminosity. Remember that Cepheid variable stars, we can oftentimes work out their actual brightness because there's a law that Henrietta Leavitt Swan worked out way back in the turn of the 20th century. So that they could be, standard candles as well. Cepheid variables, type 1a supernova, certain objects, known brightness. So we got the known brightness. Now we're going to divide it by 4 equals. I like to chip away at it one sort of piece at a time. So I divide by 4 first. I'm going to divide by pi equals. So I got rid of my 4, got rid of my pi. Now I got to divide by this. So divided by, open parentheses. You must use parentheses, grouping symbols. When you go to type in a value like this, times 10 raised to the negative 9. When I close the parentheses, I can sort of see, yep, that's the 2.6 by 10 to the negative 9 quantity that I'm dividing by. Without using grouping symbols, the calculator will divide by the 2.6 first and then multiply by 10 to the negative 9 next, which gives you a incorrect answer. So that's what we have under the radical. And then we need to take a square root. So I could either hit this button, which will take a square root, or I could raise it to the 0.5 power, right? So raising something to the 1/2 power is the same thing as taking a square root. See that? So you get a calculator value of everything you see up there. Why this just equals 3 quintillion, 832 quadrillion, 913 trillion, 450 billion, 128 million, 368,614, let's say. Obviously way too precise, right? We don't know it to the meter. The best we can do is maybe 2 significant digits. And so we'll round this 3.8 by 10 to the scientific notation review, 3, 6, 9, 12, 15, 18 decimal places. We're sliding this, the decimal is here, right? So we move it over 18 places to put it there. And that's why it's 3.8 by 10 to the 18 meters. There is your first calculation, the first 3 marks. Keep a good thing going here. And move right on down to this one, which you may recall or you may not recall that when we covered the lesson on the Big Bang Theory, we talked about the ultraviolet catastrophe that occurred until Max Planck came along and said, here's the law that we need that gives us the correct spectrum, right? And so the Veen Displacement Law basically is this one up here that tells us how the temperature relates to the maximum sort of peak wavelength for a black body. So like for a star, wherever this starlight is peaking, it's related to the temperature, right? So red stars sort of peak in the red, yellow stars peak in the yellow, blue stars peak in the blue, and you can see how the temperature sort of relates to that. So temperature is related to 1 over the maximum wavelength. We don't really need to know the constant up here because we can set this up as a proportion. They give us the sun, right? And I think that their value sort of agrees with this one. So this is the sort of physics that we need here. You might, if you have really detailed notes, you might have found that in your notes, but that was probably the toughest one on this quiz here. So let's see what this is going to look like mathematically. It says explain your reasoning. And so the reasoning we need, again, is called the Veen Displacement Law. That's how you spell Veen. And it says that the temperature is proportional to 1 over the maximum wavelength, or you could also say that like the maximum wavelength is inversely proportional to the temperature. All right. We want to really solve for the distant star. It says show that the surface temperature of this distant star is approximately this. So we'd like to calculate that and then compare it to this value and see, okay, we should get this for an answer, right? So they're saying for the sun peaks at 500 nanometers. There's its surface temperature. This distant star, we can measure its spectrum and we can, deduce that it's got a maximum peak wavelength. It says the maximum rate of emission occurs at 430 nanometers. And so this is the distant star, and we want to show how that's going to give us this temperature. So I want to set this up with temperature sort of in the numerator, and I want to set it up with this temperature in the numerator. So think about it like this. Here's the temperature of our distant star. Okay, we'll just use that. Over the temperature of the sun. So we set up a ratio here. And because it's inversely proportional, we say, okay, well, the sun's temperature is going to go down here. We're going to make this an equation now. So by comparing sort of these two, the temperature of the sun is inversely related to its peak wavelength. And so that's going to go up here. 500 nanometers is the sun's peak wavelength. And so it goes up in the numerator because I put the sun's temperature in the denominator, which means that the peak wavelength for my distant star, right, inversely proportional to its temperature, is going to go down here. It's okay to leave it as nanometers because those units are just going to cancel out. And well, you know, since I plugged in values here, I might as well just plug in the temperature of the sun, 5,800 Kelvin, and there's your solvable equation for deducing the temperature of this distant star. So you're going to take the ratio 500 to 530 and multiply it by 5,800, right? If we multiply both sides of this by 5,800 Kelvin, 5,800 Kelvin, our units here cancel, nanometers cancels, and we're left with degrees Kelvin. It's just a matter of queuing up your on-screen calculator. There you go. And crunching some numbers. So we've got, where can I do this? Well, I guess there's as good a place as any. 500 divided by 430 equals times 5,100. And indeed, we get something pretty close to what they said that we should. We solve the temperature of this distant star as 6,744, which is indeed about 6,700 Kelvin. So checks out. All right, and so you just kind of need the reasoning of the Veen, it's called the Veen Displacement Law, which again just relates the temperature to the maximum peak wavelength. Math people can double check me on this, but I believe that you are taking the derivative of this guy down here to get that. Okay, the derivative of the Max Planck radiation law gives you that. I'm not 100% sure about that. If you know better, leave it down in the comments below. And then finally, we're going to use the information in A and B1 to determine the radius of the star. So there's only certain information that's helpful in determining the radius of the star, and it is not the flux, but rather the luminosity. So the luminosity is one thing that's helpful to know here. So that's the information in A that we want, 4.8 by 10 to the 29. So the information in A is that the luminosity is 4.8 by 10 to the 29 watts. Okay, so keep that in mind. And then B1 tells us that the temperature is approximately 6,700 for this star. So I'm curious to know, did anybody find some notes where they were able to relate the radius of a star to some of the information that's sort of given here? This was another kind of tricky one, but it's the most recent one I think that we've covered. We did that distance flux thing way back at the beginning of the course, you know, back in January. But this one we've covered more recently. Let me go ahead and jump that real quick so I got more room to work here. And so hopefully you were able to scour your notes and find the Stefan Boltzmann law, which says that the luminosity of a star is going to be equal to its area times the Stefan Boltzmann constant times temperature to the fourth power. This is where we said it's a high power law, that if you double the temperature, you're going to double to the fourth power, or make the luminosity 16 times brighter, right? So the luminosity goes as the temperature to the fourth power. This is the area of the star, the entire surface area. And just like we saw earlier, that the surface area of a sphere, 4 pi d squared. And so here it's 4 pi r squared. And that's how we'll get to the radius. when Sirius B, the first white dwarf star, was discovered, it was found in its spectrum that it is way hotter than Sirius A. Sirius A is the brightest star in the night sky. And you can't even see Sirius B with the naked eye. And so the only way to explain that, like it should be a lot more luminous, right? If it's way brighter than Sirius A, why isn't Sirius B brighter? Because its area is so low. That's why it's a dwarf star. So we can deduce sort of the physical size of these using a law like this. And this gives us a clue about how tiny a star like Sirius B must actually be. So that's the area there. We've got the Stefan Boltzmann constant. We've got temperature to the fourth power, and that's going to be equal to the luminosity. So we're going to rewrite this equation to make R the subject, right? We're solving for the radius. And so we'll divide by everything besides the R squared. So 4 pi sigma t to the fourth, 4 pi sigma t to the fourth. Get rid of those 4s and pi's, get rid of those sigmas and t to the fourth. We got an R squared equal to the luminosity over 4 pi sigma t to the fourth. And then we'll take a square root. Remember, raising something to the 1/2 power is the same thing as taking a square root. But sometimes that's easier to type in your calculator. I think we're ready to substitute in some values now. Remember that the information in A was that the star was, I can't remember now, I think it was 4.8 by 10 to the 29. Yeah. So the luminosity, 4.8 by 10 to the 29 watts over 4 pi. The Stefan Boltzmann constant, if you have really good detailed notes, maybe you found it's 5.67 by 10 to the negative 8. I just remember it 5.678, but you got to remember there's a negative there. So 5.67 by 10 to the negative 8. And then you can always kind of use this equation to figure out what are the units of the Stefan Boltzmann constant. So I just sort of think about it like luminosity is measured in watts. And I've got an area and I've got a t to the fourth over here. And so the units of sigma must be watts, but then I got to get rid of the units of these other things. And so the units of sigma are watts, so it agrees with this left side of the equation, but I got to cancel out the units of area, meters squared, and I got to cancel out the units of temperature to the fourth. And so those are the units of sigma. 5.67 by 10 to the negative 8 watts per meter squared per Kelvin to the fourth. These here are the units. And I just like to move these in the denominator back up to the numerator, right? So that's sigma. And then you've got the temperature, 6,700. Remember, that was the information in B1 that they told us to sort of show using the Veen Displacement Law. That's in Kelvin, and that's to the fourth power. So you can kind of see that the Kelvin to the fourth powers are going to cancel, the watts are going to cancel. And once I take the square root of meters squared, I'll have meters of radius, right? So again, the units are a nice sanity check on your calculation. It should all work out to give you what you expect unless you made a mistake. Back to the old calculator. Do this up just a bit here. All right. So we've got the numerator, 4.8 times 10 to the 29 equals, divided by 4 equals, divided by I equals, divided by 5.67 times 10 raised to the negative 8, close parentheses, equals, divided by 6,700 raised to the fourth power, big number, equals. So I get, oh, I get the answer that's underneath the radical, right? So all I've done so far is taken this and divided by all these things, but I still have to take the square root of it, right? And so that's the answer underneath the radical. We'll go ahead and, or remember, either take the square root or raise it to the 1/2. Let's raise it to the 0.5 or the 1/2 power to give me a final calculator value that I wouldn't write on this line, right? I wouldn't report this value, but I can sort of say, okay, my calculator shows me 18,284,140,583. It's rounded to the ones place. And so this is going to be 1.8 by 10 to the 3, 6, 9, 10. 1.8 by 10 to the 10 meters. 7 total marks. Tally them up. Send it to me. But let's also go over our final exam. I'll do that on a separate video.